Hello everyone. Now we will continue our learning on rock properties. Previously we have learned about porosity and now we will talk about permeability. Okay, permeability or with the symbol K by definition is a measure of the ability of a rock to allow fluid to flow through it. The unit is in millidarcies or darcies. Most commercial reservoirs have permeability ranging from 20 millidarcies to 500 millidarcies, where tight reservoir has permeability of zero point 0.1 to around 1 millidarcy. Okay, and here is another classification. Permeability below 1 millidarcy, we call it poor reservoir or poor rock. 1 to 10, fair. 10 to 50 millidarcies, moderate. 50 to 250 millidarcies, good. Good reservoir, good rock, good property. And 250 millidarcies or more than, I think this should be more than 250 millidarcies. We call it very good rock, very good permeability. Okay, permeability based on the lithology. As you can see here, we have three type of rocks. Okay, the first one is shale, the silt, and the sand. And based on the picture, you can distinguish, you can differentiate, you can tell that shale will have the lowest permeability, and then the silt, and then sandstone will have the highest permeability. Okay, because by definition, permeability is a measure of ability of a rock to allow fluid to flow through it. So as you can see in sand, if we zoom in, here the white area, white zone is the space through which fluid can flow. And you can see this white zone, we can call it roughly the permeability or the connected porosity. And we have many channels here. But here it is very tight. The channel, the permeability or the space that enable the rock to flow fluid is very, very small. So shale will have very low permeability, but sandstone can have high permeability. And then based on theoretical experimentation, we can get permeability using this experimentation. This was done originally by Mr. Darcy, from whom the unit millidarcy, we get the unit millidarcy. So Mr. Darcy conducted this experimentation. He has this connected pipe, the first one with the reservoir in the right side and then the left side. And he made this pipe to be like this with distance between the surface on the right storage or right tank and the left tank. There is a distance, and we can convert the distance to delta pressure, okay, because they are connected. And this is the area of the pipe, okay, area of the pipe. And here we can put a core or rock with length of L. And from the right tank, we flow fluid, for example, maybe water, okay, with viscosity that we know. And then we measure the flow rate here. And based on this experimentation, Mr. Darcy concluded this formula. So delta P divided by L, the length of the core, is minus 887.2 multiplied by the flow rate Q and the viscosity of the fluid divided by something multiplied by the area. And this something is actually the permeability. Okay, using this experimentation, he obtained a linear pressure gradient. So P input here, the input, and P output here, and P in minus P out, we get delta P. Okay, and this is the length from length 0.0 to L. So the total length is L, and he get this linear pressure gradient, okay, with this flow configuration, okay, this linear flow. So again, this experimentation or this correlation can be obtained, can be generated with this term permeability, okay? Or this is another depiction. We have pipe and we put core inside the pipe with area of A. So we can call it the A, area of the flow, okay? And flow rate Q, and we can measure the pressure difference, delta P, from P1, input pressure, and P2, output pressure. And again, the correlation is this. And we can arrange the mathematical formulation so we can get the permeability here. So permeability is the flow rate multiplied by viscosity multiplied by the length of the core divided by the area of the flow, okay, cross-sectional area of the pipe multiplied by pressure difference. So that's K, permeability. So this is quite simple, okay, quite simple permeability of this core of this rock. We measure it in the lab, but of course in reality, the permeability that influence the reservoir performance is the permeability average throughout this reservoir zone. Okay, so in this case, in laboratory, we have flow rate from the right to the left, but here we have flow rate of the field. Okay, we have the flow rate, and this flow pass through this reservoir. Okay, so the dimension is huge in the real reservoir. Okay, but the definition is still the same. Permeability of a rock or permeability of the whole reservoir, okay, is the ability of the rock or the reservoir to enable fluid to flow through it, to flow through the rock, to flow through the reservoir. Okay. If you have high flow rate, you will, if you have high permeability, you can get high flow rate. If you have low permeability, you will have low flow rate. Kalau permeability kita tinggi, oke, aliran bisa lancar, aliran bisa deras. Tapi kalau permeability-nya rendah, aliran bisa mampet, bisa sangat kecil, seperti itu. Oke, factors determining permeability, there are many factors. Pore size, of course, pore size distribution, grain size distribution, the shape of the grain, cementation, and compaction, which is function of pressure. Okay, so factors determining porosity, many factors are also determining permeability. Okay, so you can go back to the porosity chapter and you can see how pore size and pore size distribution and the grain size will influence the porosity. And in more or less the same way, these factors also determine the permeability. Oke, so jadi inilah faktor-faktor yang mempengaruhi permeability akan besar atau kecil. How to measure the permeability? Of course, using core. We can perform experiment in the lab. We can conduct run flow tests. And then we can solve Darcy's law to obtain absolute permeability, like the experimentation that was carried out by Mr. Darcy. Okay, this is permeability from the core. But from engineering point of view, we can also get permeability from well testing. We do that on the field. We will measure the flow rate and the pressure, and then we will perform well test analysis, okay, or pressure transient analysis to obtain the effective permeability. Okay, so from core, we can get absolute permeability, but from well testing, we can get effective permeability. And of course, there is relationship between porosity and permeability. And in real job, we usually create correlation like this. We get porosity data, we have permeability data, and we make this plot. We make this plot, porosity and the permeability, okay? And we have these dots, and then we can regress, we can conduct regression, trend lining, and we have this blue line. These red dots are the measured permeability, and this blue line is estimated permeability, okay, by correlating the permeability and the porosity, okay. So this is the porosity and permeability relationship, which is very, very important. So if you have porosity, you can predict your permeability and vice versa. This is another example of the correlation or the relationship between porosity and the permeability. And you can see here we have three classes. This is the correlation for class 1, this is for class 2, and this is for class 3. This is usually done by geologists or petrophysicists, so we can obtain or we can get the correlation from them. Okay, so they are the ones who generate this correlation. They are the ones who want to know the relationship between the permeability and the porosity. Okay, so we call it cross plots. Cross plots are often used to, to estimate permeability from porosity data or to populate a 3D reservoir model with permeability value based on porosity data or maps. So for example, if you have porosity data, if you have many porosity data or you have porosity map, then you can just estimate the permeability from the porosity using this equation or using this correlation. Jadi kita bisa dengan mudah mengestimasi, memperkirakan permeability-nya berapa kalau kita punya porosity. Yang penting kita bisa buat dulu this correlation, this equation, or this relationship. Okay, this is another depiction. This is for clean sandstone. It's quite regular. You can see the trend line. We can also call it, this is for homogeneous sandstone, or maybe we can call it, yeah, homogeneous. But for carbonate, it can be very, very heterogeneous. So it can be very, very difficult to create or to see correlation between porosity and permeability. Okay, because in sandstone we usually have primary porosity, okay, but in this carbonate we usually find secondary porosity, fracture, something like that. So sometimes it can be very difficult to find the correlation between the porosity and permeability. And for this carbonate, we need to go deeper and deeper. We can classify the carbonate into several classes, maybe several rock types, so that we can distinguish the correlation or the relationship between porosity and permeability for each rock type. Okay. Another picture. This is porosity in linear scale plotted against Klinkenberg permeability in log scale. You can see poro-perm relationship for different lithologies. For fractured rocks, for crystalline cemented sandstone, oolitic and coarsely crystalline carbonates. This is for clean sandstone, finely crystalline carbonates with flux, clay cemented sandstones and chalks. And you can see for clean sandstone, it's quite, yeah, it's almost 40 degrees, okay, the slope visually. Okay, so we have from low porosity to high porosity with the same from low permeability to high permeability. But for fractured rocks, with only small porosity here in fractured rocks, for fractured rocks, although we have porosity, although we have small porosity, the permeability is big. This is because we have fractured rocks. Small porosity, but high permeability. Okay. But for clay, cemented sandstones, and chalks, we can have high porosity, but the permeability is small. For chalks or cemented clay, cemented sandstones, you can have high porosity, but permeability low. Okay. So again, porosity permeability relationship for each lithology, for each class, for each category, or for each rock types is very, very important. Porosity permeability relationship influenced by diagenetic process. So if your rock experience dissolution, then you can you can experience this change. You have low porosity and low permeability, but because of dissolution, maybe because of water, because of acidic water, porosity can be big, okay? Permeability can also increase, okay? But if we have cementation or silification, it is another way around. First, you can have high porosity, high permeability, but because of cementation, because of silicification, the porosity and permeability can be reduced because of this diagenetic process. Okay. For dolomitization, this can be two ways, both ways. Can be increased and can also be decreased, both the permeability and the porosity. If we have flux, then we can move like this way. The porosity can be increased significantly, but the permeability will not increase significantly. But if your rock experience fracturing, maybe because of tectonic process, the porosity can be more or less the same, but the permeability can increase dramatically. Okay, so this diagenetic process is really, really important. So as engineer, as geoscientists, we need to understand what happened in our reservoir. Is there any diagenetic process occurred in this reservoir? This is the petrophysical analysis of core samples to identify flow units. This is another depiction of poro-perm relationship. So for example, we have this core. We start from the left. We have this yellow area and then a little bit orange and then yellow again, orange. We get that from the rock. And based on the characteristics, the physics, the textures, the visualization of each rock, we can divide them into several lithophases. We have this 1, 2, 3, 4, 4 lithophases. And from this body of rock, we take core plugs. We have core plugs 1, 2, 3, and 4. They are different. And then we analyze using microscope, and then we see the pore types. So for the first class, it's like this. You can say it's high porosity, high permeability, and then this one lower permeability, lower porosity, and then this one poor reservoir, and then this one the lowest porosity, lowest permeability. Okay, they are disconnected. The porosity, yeah, you can see the porosity and the permeability is very small from here. And then using this data, using this permeability and porosity from each experimentation, from each measurement, we create this plot. Petrophysical data, we can create this plot for porosity versus permeability. And for the first rock, we have poro and perm here. So porosity high, permeability high, and quite homogeneous. And the second class, quite high porosity, quite high permeability, but more heterogeneous. The range is bigger here. And this one, moderate porosity, moderate permeability, and this one, the fourth class, low permeability, low porosity. And we can also create the capillary pressure plot. We will learn about this in next few weeks, capillary pressure. And then we also check the gamma ray. And the gamma ray, the trend is like this. So clearly they are different. From the gamma ray log, we can clearly see that they are different. And lastly, we make conclusion. Flow units from high quality to the lowest quality, we have finally 5 or 4 classes, but this one, and then fourth, third, number 2, and number 1. And more or less, number 4 and number 2 are quite similar. But finally, you can say you have 4 types or 5 types based on this analysis. So you see, this is very, very important because ultimately this will influence our reservoir simulation. Because in reservoir simulation, we will have porosity, we will have permeability, we will have capillary pressure that will influence our simulation. All right. And although porosity and permeability relationship is very, very useful, it has limitation. And these are the limitation. The plots are constructed using laboratory or core data. Okay, so you see core is very small. So actually it is very, very limited. Maybe it cannot represent the reservoir, the entire reservoir very well. So basically you need to have many cores. And typically correlations drawn on logarithmic plots yield conservative or low permeabilities. Okay, so the plotting technique is also important, and it can also be the limitation. Whether we plot it using linear scale or logarithmic scale or semi-logarithmic scale are very, very important. High permeability sense may be missing from the core, and we need to match or check with well-test data or production test results wherever possible to recheck the observation with core data. So core data measurement or core measurement is not enough. Okay, we need to check the well test. We need to check the production. Okay, to confirm the conclusion from the laboratory or core measurement. And then the average permeability. Okay, you see that the reservoir is very, very heterogeneous, and we have many permeability values. But at the end of the day, we need to do averaging to get only one or only reduced or average permeability. And there are several ways to average the permeability. The first one is like this. So if the flow direction is like this, and you have, for example, three layers, layer 1, layer 2, and layer 3, with permeability 1, permeability 2, permeability 3, with different thickness, thickness 1, thickness 2, thickness 3, flow direction like this, for example, we can call it parallel flow. This is the schematic parallel flow through three layers with different permeability and different thickness. Okay, linear flows through layered parallel beds. We can average the permeability using this method. And the method is called arithmetic averaging. So permeability 1 multiplied by thickness 1 plus permeability 2 thickness 2 plus permeability 3 thickness 3 all divided by total thickness H1 plus H2 plus H3. Okay, this is the arithmetic averaging, and you need to know this. Okay, another depiction of the arithmetic averaging, but with different configuration. It's still parallel, okay, linear flows via layered parallel stratums with different area. So you have layer 1, layer 2, layer 3 with different permeabilities, K1, K2, K3, different thickness, H1, H2, H3, and different width, W1, W2, W3, or different area 1, area 2, area 3. You can average the permeability, okay, by weighting on the area instead of the thickness. So you see K1 A1 plus K2 A2 plus K3 A3 all divided by total area A1 plus A2 A3. Okay, and A1 is calculated using this one, H1 thickness 1 multiplied by width 1, okay, or HI multiplied by WI. Okay, this is also arithmetic averaging, but area weighted, okay, weighted based on the area. Previously, this is the weighted based on the thickness, okay, because they have same area of the flow. This is harmonic average permeability. So this is beds in series harmonic average. So the configuration is like this. This is not parallel flow. This is series flow with layer 1, layer 2, layer 3, like this one. Flow direction from the left to the right, linearly. You have layer 1, layer 2, layer 3, K1, K2, K3, length 1, L1, L2, L3, with the same thickness, but of course they will experience different delta P. So you have delta P1, delta P2, delta P3, okay? And we perform harmonic averaging to get the average permeability. So first we sum all the length, L1 plus L2 plus L3, all divided by the summation, the total of L per K for each layer. Okay, so at the top, at the numerator, di pembilang, we have L1 plus L2 plus L3. And for the denominator, the penyebut, kita tambahkan L per K di 1, L per K di 2, L per K di 3, kita tambahkan, baru akhirnya kita bagi. Then we have harmonic averaging. Okay. And this is harmonic average permeability, but for radial flow. Again, it is beds in series harmonic average. You have the flow rate here, okay, and you have the drainage radius, RE, but you have radius 1, radius 2, radius 3 with the same thickness. And here you have your wellbore radius. Then you can perform this harmonic averaging using this formula. Again, this symbol is called sigma or the summation. Okay, you need to know this, you need to understand this because I might ask this in the test. Okay, so it's very, very important because this averaging method is also used in the reservoir simulation. Okay, because the permeability in the model is heterogeneous, they are all different, there is no purely homogeneous permeability where the permeability is exactly uniform. There is no such case. So there will always be averaging method. Okay. This is also harmonic average, but for very, very, very heterogeneous. So they are irregular in shape and in depiction we can depict it like this schematically or can like this K1, K2, K3, K4, 5, 7, 6 with different shape, different area, different thickness, different permeability, different properties. The beds are randomly distributed. We can still try to average the permeability using this equation. If all cores have the same thickness, then the averaging can be like this, just K1, K2, K3, all the way through Kn, and all of them powered by 1 per n. N is the total number of samples. Or if the thickness are different, then it can be like this. Okay, so first you need to sum all the thickness multiplied by the logarithmic natural of the permeability divided by total thickness, and we do exponent. So this is not ESP, but EXP, exponent. Okay. So this is the another depiction. First, if you start with arithmetic averaging and then continue with harmonic averaging, then it will be like this. If you have this 16 layers or 16 units, you start with this one, different permeability with different length, different thickness. You do arithmetic averaging, arithmetic mean, then you will have this 4 layers with different length. Okay, but they have same thickness. Okay, and then you do harmonic averaging, then you will only have one average permeability. Okay, so this is very useful. You can simplify this heterogeneous rock into one homogeneous rock, but it is average. So we can also say this is realistic, but this is the model because this is not real rock. This is calculated rock using averaging method. And this is arithmetic approach, arithmetic mean, arithmetic average. This is the harmonic average. Okay, so you can see clearly the expansion of the formula of the equation. So it's quite easy actually. But you can also start from harmonic and then end with arithmetic. Okay, the result can be the same, can be different. Okay, but the difference will not be too big. Okay, you start from here, you do harmonic mean, then you will have four, for example, four permeability, four layers, but with the same length and different thickness, and you do averaging, arithmetic averaging, then you will have one value, one average permeability. If you have this in your simulation, then the simulation can be too long. the calculation can be too long. But if you have only one value, the simulation can be significantly faster. Okay, so averaging is very, very important in our simulation or calculation. This is empirical correlation to estimate the absolute permeability correlation if you have porosity and if you have Connaught water saturation. So you can have, or you can use Timur equation for hydrocarbon bearing zone. You can also have Morris-Biggs equation for oil reservoir. But for gas reservoir, Morris and Biggs also have another equation. You can use this. You can also use Ahmed equation, provided that you have porosity and then this Connaught water saturation, right? And permeability will be in millidarcy, porosity in fraction, not in percent, and Connaught water saturation also in fraction, not in percent. So if you use percent, then the formula will be changed. You need to modify the formula, but this formula, these equations are for porosity and Connaught water saturation in fraction. Okay, so be careful in that. For example, absolute permeability correlation. Estimate the absolute permeability of an oil zone with Connaught water saturation and average porosity of 25% and 19% respectively. Okay, so again, this is for absolute permeability. This is not for effective permeability. Okay, all right. Okay, all right. So for Timur equation, you use this formula. You use this formula, but see, we change the Connaught water saturation from percentage 19% to fraction 0.19, and also the porosity we change it from percent to fraction, so from 25% to 0.25 in fraction, and we apply Timur equation, we get permeability of 92.1. And then we also can calculate with Morris and Biggs, and we get the permeability to be 47 millidarcy. And which value we need to use? Usually I just do averaging, arithmetic averaging. So Timur permeability plus Morris and Biggs permeability divided by 2. So you just average the Timur and Morris and Biggs permeability to get the final average permeability. Okay, but it depends on the engineer. If you want to use Timur only, then you can use 92.1. If you prefer Morris and Biggs, then you can use 47. But for me, basically, usually, I just do averaging. Okay. But in cases that I know for sure that Timur equation is more applicable, then I will use Timur. But for cases where Morris and Biggs is better, is more applicable, then I will use Morris. If I'm not so sure, then I can calculate in two methods and then average. Okay, so that's all for permeability. We will continue with saturation. Okay, this is the next rock property that we will discuss. Okay, thank you.